Okay, let me review some contents in previous session until other students coming to class. In this chapter, we see the sorry, let me record this. Okay, Muhammad, do you have my voice? Okay, let me review some content in the previous sessions. We see the definition of representation. Let G be a group and K be a field. We consider always K equal to real or complex numbers, okay? A linear representation of G defined over K is a group homomorphism rho from G to GL of E, where E is a K vector space and this is the set of all linear and bijective function from E to E, okay? And the dimension of E is called the dimension of rho. We see some example for representation on a group G with different vector spaces E, okay? And also we see this notation. It is very nice that if we have a representation on G, we can induce an action of G on E, okay, by these function rules. Please note that. If rho, for example, from G to GLE is a representation, then we have the following action of G on E. This action from G times E to E by these function rules. G and X, for example, or V, for example, V map to G dot V, and this is equal to rho of G of V. This is this notation, okay? Rho of G of V, because we know that for any G in this group, rho of G is a function from E to E, so that rho of G of E of V is an element of E, and we can define this action of G on E. And by this action, we can embed G to GL of E. Okay? Any representation on G leads to an embedding from G to GL of E. For example, we can fix a vector such as V, then we can map any G to rho of G. Any G map to rho of G. Okay. And in the following we see some examples. And this definition, faithful and trivial, representation, let G be a group and let K be a field. A representation rho of G defined over K is faithful if rho is injective, or the kernel of rho equal to identity element only. And a representation rho of G on a K vector space E is trivial if rho of G equal to 1 for all G in G. On the other hand, the kernel of rho equal to G. Rho is called trivial if rho of G equal to 1 for all G in G, or equivalently a kernel of rho equal to whole of G. And we have this remarks and these examples that very nice and easy. And finally we see the definition of morphism. Morphism of representation, let G be a group and let K be a field. A morphism or homomorphism between representation rho 1 and rho 2 of G, both defined over a fixed vector field K and acting on the vector space E1 and 2 respectively, is a collinear map such as phi from E1 to E2. This phi is a linear map from E1 to E2 by these equalities. For any G in G and for any V in E1, we must have these equalities, or this diagram must be commutative. Okay, rho 2 of G O phi must be equal to phi O rho 1 of G. Please note that for any G in all group G, rho 2 of G is a linear map from E2 to E2, and rho 1 of G is a linear map from E1 to E1. Okay, so this diagram is well defined. And by our notations, rho 1 of G of V can be denoted by G dot V, and also G can be denoted by G dot phi of V, so that phi is a morphism if for any G in G and V in E1 we have this equality, this equal to this. These two are the same concept. Okay, it is also easy to see that the set of homomorphism from rho 1 to rho 2 as representation of G is a k-vector subspace of hom of E1 and E2, which is denoted by this. This set of all homomorphism from rho 1 to rho 2 denoted by this, and this is the subspace of this space. We have this proposition that is very easy. Let G be a group and K a field for any representation rho of G and a vector space E. The identity map on E is a homeomorphism from row to row, and given representation rho 1 and rho 2 and rho 3 on E1, E2, E3 respectively, and this morphism, this composition phi do or phi ek from E1 to E3 is a morphism between rho 1 and rho 3. Let me write this for you. Let G be a group one for any representation such as rho from G to GLE, for example, the identity map such as I, for example, okay, from E to E is a homeomorphism between row and row, okay, and this proof is easy because we must check these equalities, okay, these equalities for any G in G, because for any because for any G in G and V in E, we have identity of row G of V, identity row G of V, okay, equal to, this is identity map, so that this is equal to row G of V, and this is equal to row G of IV, because this is identity map again, okay, so we have this equality, phi of row 1 of G of V equal to row 2 of G phi of V, because phi equal to the identity map and row 1 equal to row 2 and equal to row, okay, so that this is very trivial. And also if we have two representation such as three representation, three two if row 1 from G to GLE1, row 2 from G to GLE2, and row 3 from G to GLE3 are three representation and Phi1, for example, okay, from E1 to E2, and Phi2 from Phi2 from E2 to E3 are representation homeomorphism, not representation. Homomorphism or homomorphism between E1 and E2 and E2 and E3 respectively. Then Phi2 or Phi1, obviously from E1 to E3, is a homomorphism between E1 and E3, and its proof is easy again, because for all G in G and V in E1, we have Phi2 or Phi1 please note that we must check this equality, okay, and we have phi2 or phi1 instead of phi2 or phi1 of rho 1 of g of v, rho 1 of g of v, okay. This is equal to phi2 of phi1 of rho 1 of g of v, okay. But this is equal to phi2 of rho 2 of g of v1 of v, because rho 1 is a representation, okay. Because rho 1 is a where phi1 from e1 to e2 is a representation, okay. And this is equal to because this is an element of v, okay. This is equal to rho 3 of g of phi2 of this element, phi1 of v, okay, because this is an element of v again, okay, an element of e2, phi1 is a function from e1 to e2, so that this is an element of e2. Is because phi2 from e2 to e3 is a representation, okay. And the last one equal to rho 3 of g phi2 o phi1 of v. So we have this equality for this morphism between rho 1 and rho 3. So this proposition is very easy, and we have these two facts. And also we have this remark Dear students, you have my voice? The category of representations in the language of category theory, which we will only use in remarks in this book. Okay, this proposition states that the representations of a given group G over a given field K are the object of a category with morphism given by the intervening linear maps. In a morphism, phi is a bijective linear map. Its inverse is also a morphism between row 2 and row 1. Please note that phi is a morphism from row 1 to row 2, and its inverse is a morphism from row 2 to row 1, and it is therefore justified to call phi an isomorphism, not morphism, okay, between row 1 and row 2. Indeed, using the diagram above, we find that the relations row 2 of G O phi equal to phi O row 1 of G, or equivalently we have this. It is very easy because we can combine two sides of this equality with the inverse of phi. Okay, row 2 of G O phi row 2 of G or by this equality phi O row 1 of G. Okay, phi O row 1 of G equal to row 2 of G O phi, so that phi inverse O phi O row 1 of G equal to phi inverse O row 2 of G O phi, and this is identity map, so that row 1 of G equal to the inverse of phi O row 2 of G O phi. And also we can consider composition of this with the inverse of phi, row 1 of G O the inverse of phi equal to the inverse of phi O row 2 of G O phi O the inverse of phi, the inverse of phi, but this is identity again, and this is equal to the inverse of phi O row 2 of G. So we have this equality. We have this equality. Okay? And also if we consider the restriction representation that we defined in the previous sessions, that F be an invariant subspace of E. Okay. Remark. Let be an invariant subspace of E with respect to the representation rho from E to GLE, for example. Okay, so that for any G in G, rho G of F must be a subset of F. Okay, and rho tilde from G to GLE of F be the restriction representation on F. So let me write this by another color. For any G in G, rho tilde of G, and also let me write this, and for any V in F, rho tilde of G of V equal to rho of G restriction by F of V. Okay. And we know that this is an element of F because F is invariant subspace. Okay. these two are some additional comments. Okay. Then if we consider this restriction representation, then the inclusion map inclusion map for example I from F to E by this function rules I of V equal to V. Okay, for any V in F, let me write this by another notation such as G. Okay, different from the identity map. Okay, is a homomorphism between row and row tilde, and its proof is trivial because for any G in G and for any V in F, we have J of row 1 of G of V equal to row 1 of G of V. Because this is inclusion map by this function rules. Okay, G of V equal to V, and this is equal to row 1 of G of V. And G of V is an element of F, so that this is equal to the restriction of G in F of G of V, and this is equal to row tilde of G of V, so that we have this equality again, this equality for the inclusion map instead of V, and row tilde instead of row 1 and row 2. And also we have this example, trivial sub-representations. Consider the case where F is the of all vectors v which are pointwise invariant under G. Or more carefully, for any v in F, v belong to F if and only if G dot v equal to v for all G in G. And we denoted this by EG. Okay, let me write this for you. Notation. Let rho from G to GLE be a representation and EG by this notation equal to the set of all vectors in our vector space E such that for any G in our group G dot v equal to v, or equivalently the set of all v in E such that for any G in our group G, rho G of v, okay, because we know that this is rho G of v, rho G of v equal to v. It is very trivial that this is a linear subspace of E. And this is a sub-representation of rho and the representation of on this space is trivial. All of this is very trivial. E.g. is a linear space. It is very trivial because if we have this equality for V1 and V2, this holds for V1 plus V2. Okay, and other statements are very easy. Let me add another page. EG is a subspace of E, because if V1 and V2 belong to EG and alpha be in our scalar field, then for any G in G we have rho of plus alpha rho of G of V1 plus rho of G of V2, because rho is a linear map, so that for all G in G is equal to rho G of alpha plus V2 equal to rho G of V1 equal to V1 and rho 2 of G V2 equal to V2. This is equal to alpha V1 plus V2, because this is equal to V1 and this equal to V2. And this shows that alpha V plus V2 is an element of G. Okay. So E is some representation if you consider restriction of these two EG. Rho theta equal to the restriction of rho in EG. Is a sub representation of rho. This is a sub representation of rho. We must this equality, and we see this in the general case. In previous example, we see this for the restriction presentation. Okay, we see this for the restriction, and also we don't need proof this again. We see this, okay, arbitrary representation, and we have this a special case of invariant subspace. It is very trivial that G A is invariant subspace of E, because let me write this. EG is invariant with respect E, because for any G in G and for any V in EG we have rho of G of V equal to G dot V, and this is equal to V, and V is an element of EG. It is very trivial, okay? Okay. And also we have this observation that we can embed complex number or field number on or field in all vector space E. This space of invariant is the largest sub-representation of E, which is trivial. More individually, any non-zero vector V, which is invariant under G, define a trivial sub-representation of dimension 1, i.e. an injective morphism by this. Please note that if we fix if belong to E, we can define a function h, for example, okay, h from or complex number or field, okay, or field C, R or K from E. By this function, any element such as alpha equal to alpha v. V is a fixed element, okay. This for any alpha in our scalar field, we define this. Then h of k is a one-dimensional space in E. This is the vector space generated by one element V, okay? V in our vector space E. This one is meaning whole of vector space K. And by this embedding, we can define this isomorphism, or if we denoted this by, for example, HV, okay, HV. Now if we define for example psi from EG psi from EG to the set of all homomorphism from K to E. By this function rules, psi of V equal to HV for any V in EG K to E. Okay, this is a isomorphism, and EG is can be identified by this set of homomorphisms. Okay, dear students, in the next session, okay, shukran and goodbye.